using observational data sets.
Do I have a pointer? Okay. Hi everyone, I'm Kameswara Mantha. I'm a graduate student at UMKC. And today I'm going to talk about major merging using observations, and also I'll be discussing about probing tidal features that may be due to galaxy mergers using simulations and also using HST. I would like to mention that the work that I'm going to talk about here is mostly underway, so most of it's in prep. So before jumping into my topic today, I would like to give a short recap because the current talk is a sequel to my previous talk that I gave yesterday. Since most of you guys weren't here yesterday, so I'm going to give a really brief overview of what happened in my previous talk. So what I did is I tried measuring major merger rates using closed pair statistics within the CANDELS fields observationally, and my main punchline of the talk is here, which concluded that closed pair observability timescales play a very important role in your estimates of major merger rates. For example, here are two plots where on my y-axis I have major merger rate, which is essentially the rate at which galaxies are merging. It's a function of redshift, and when you measure your major merger rates using your mass ratio, you find that they're actually diminishing at higher redshifts and based on a constant timescale assumption, and they're disagreeing with theoretical predictions over here by a factor of 5. You use a simple constant timescale, whereas recently some studies have motivated evolving timescales, and if we use that, they tend to agree with the simulations more well. Now, here I plot a confusion matrix up top saying that, which essentially says that you are limited by the knowledge of your time scale in order to say for sure what is my major merger rate evolution. So this is all fine. This is based on closed pair method, but it is really important to measure the same thing in a different way or using a different method, which comes to my the topic of this talk is pursuing a different approach of probing major merging or galaxy merging. So what are some alternative methods? Here are some examples in the literature that I could find that can actually isolate mergers according to their statistics. One is the CAS and GNM20 methods, which is a quantitative approach of isolating mergers here, and the other straightforward method is to use visual classification. So you can look at an image and say if it looks like a merger or not. So these are all fine, but I would like to point out that tidal features that are caused due to interaction between two galaxies are hallmark when it comes to the process of merging. So it would be very nice if we can use them in order to identify mergers. So in the literature, there has been very little amount of work done on quantifying them very carefully. One among the few is this tidal parameter from Tal et al, which does an okay job, but is severely contaminated from non-merging sources in its identification. So what my aim here is to quantify this in a different way and also in a robust way. I would like to point out that machine learning can be used in such cases, but I would like to identify them in an independent way other than machine learning. So for this purpose, I'm going to demonstrate a really simple exercise that I've done using Wheeler simulations. So here's an example galaxy chosen in Wheeler simulations, and it is a post-merger at a redshift of 3. Such that I chose it such that it has undergone a major merger at redshift of 3.17, and this is a post-merger galaxy at that redshift. Now, what I'm doing is I try to model the galaxy, and I subtract it out, and you can see here is this nice broad tidal feature that shows up. Now, if we can measure or quantify that, that's going to be awesome. So what I'm trying to do now is I plot plot an elliptical annulus between 2.5 times to 10 times my effective radii, and here in this plot I'm showing essentially the pixel values in that annulus, and I mask everything out inside and outside my annulus. And what I do is I perform an iterative sigma clipping process, and I try to pick out only those pixel values that are above my 3 sigma limit over there. And when you mark them, surprisingly, they show up they trace really well the actual tidal feature that is present there. So using that information, I actually quantify the tidal feature in terms of its surface brightness, and right here I'm showing that there. Now, after some improvement, whatever I just showed you can be used to study, I think for the first time maybe, the physical properties of tidal features. So here are some ideas that we are thinking about right now. So if you can, right now I've demonstrated that we can isolate the tidal feature. Now if we can do this in multiple wavelength bands, you could essentially like plot a UVJ diagram for these kind of structures and see and understand the physical properties of them. And one thing is, maybe can we split them into wet and dry mergers based on their color? That's just an idea that I'm throwing out. And infer possibly, the triggering of star formation, which is often linked in the literature very often. And the other thing that you can do is you can essentially expand this into many wavelengths, and you can perform detailed SED analysis on such features and try to back out important information from them. So, which I think it has a lot of potential. Now, another important thing that I'm concentrating on is once you identify them, you can, since we know what's happening in the simulation, we can actually analyze if the feature that we are observing is from merging, which need not be always true, given competing theories such as violent disk instabilities, and the competition between the merging and violent disk instabilities can be tested in the simulations if we can isolate them. That's one thing. The other important concept is if we want to measure the merger rates, and the important parameter here is the time scale, and here specifically the time scale corresponds to the tidal observability time scale, which you can quantify using the simulation. So that is one of my main aims that I'm trying to work on. Now, as a separate, I would like to supplement the analysis that I showed with the machine learning by using machine learning to identify automatically these features in large data sets to simplify our analysis. So one quick example here is convolutional neural networks are very popular in many real-world applications such as your identity recognition, thumbprint recognition, or your face recognition. And it is a very promising method when it comes to identifying features. So I'm trying to implement this, and here's a nice example. You can randomly download an image from the internet and ask the machine what it thinks, and it predicts very accurately what it is. So, which I think is really interesting. So what I'm trying to do right now is I'm trying to analyze Cirsic residuals that we have from simulations or even data, and trying to identify these features automatically using a machine, which I will use my previously described tidal feature identification, which has been done independently to funnel into this process for as a supplement. So that's what I'm trying to work on using the simulations, and also we can apply them onto the empirical studies, and we can derive merger rates in a completely different way and see how they compare to different methods. So here are my conclusions. I'll take any questions.
Time for some questions. I'll start with one. There must be some differences of what wavelength you can identify the tidal features, and is that something you're testing with the simulations?
Yes, that's an interesting question. So I haven't fully thought about it yet, but my intuition is that I would want to sort of select in one wavelength band and then essentially take that shape and use that shape as like an aperture in different wavelength bands and just count up light in the other wavelength bands, essentially like doing photometry. But you are extracting the shape of the photometry using like your one wavelength band, maybe rest frame infrared or something.
Any questions? Yes.
Accurate in terms of what? Right. I don't think I have an answer for that, accurate answer for that. But when it comes to surface brightness, the feature that I just showed you can be very well detected in JWS from the sensitivities of the instruments that we have right now. With Hubble, not necessarily we can detect it at a resolution of 3, but it may be possible at lower range, depending on the surface brightness of the feature.
Okay. Well, with that, oh wait, one more question.
Yes. Yes. Mm-hmm.
I don't think we should be the best tracer of measures.
Sure. That's a very interesting point. I would like to talk to you in trying to minimize that issue, and for sure, I would love to talk to you.
Okay, any more questions? If not, let's thank Mantha again. And I believe it is time for lunch.